All right, good morning, everybody. Any questions before we get started? You really started the project yet? All right. So continuing speaking about side channels. Today uh, we want to shift our focus to physical side channels. Physical side channels is basically similar to digital side channels, reveal information about the system. And it's, again, similar to digital side channels, the reason that we are seeing this is because the physical activity of the device is actually relevant to the signal that we are receiving on the system. We said that we have two different types of side channels, digital and physical. We talked about cache side channels extensively. We talked a little bit about the microarchitectural side channels, including the transient execution attacks. In the next few slides, I'm going to finish that part, and then we're gonna focus on physical side channels. The main group of side channels in physical domain are electromagnetics and power. We're going to extensively talk about these two types of side channels. Before actually jumping into the physical ones, let's finish what we discussed in the past two lectures, right? To finish it, but we didn't, and that was the transient execution attacks. I gave you a fairly extensive background, so now we're kind of ready to go through how actually this attack works. So remember, the last thing that we said was the reason that we have transient execution attacks is because of the speculation. We talked about what the speculation is. And we said that a speculation, an intelligent attacker can actually exploit this speculation in order to access some illegal memory lines, some memory lines that does not belong to that process. So kind of like where we stopped last time was the reason for speculation is improving the performance. I gave you one example where we had a branch, and in order to know which instruction to execute next, instead of waiting for the branch to be resolved, we can make a guess and take a guess and then just go through one path and start executing things in a speculation window. And then if we make a mistake, we can always go back and fix that issue. Otherwise, no need to take any further action. Everything is great. We can move forward. And this way, we can get a significant performance boost. Since, as I said, mostly these, modern processors has 90% accuracy of their branch predictors, which means that 90% of the time, on average, we are making the correct decision. So only 10% of the time we really need to be worried about what should we do in order to fix this issue. So when we make a mistake, we need to do the flush. We basically need to kind of, remove the impact of those instructions that we had executed in the speculation window. In order to do that, we use this concept called completion and retire. So instructions, when they go to the pipeline, they have two different states when they finish. When they're finished, they reset it complete. By finishing means that, for example, if it's an add instruction, we add the numbers together. The operation that needs to be done on the instruction. And we call that complete. But since the completion can happen out of order because maybe there's a branch, we make a guess, we start running things out of order, and at some point we might make the mistake and we need to go back. So as a result, once the instructions are complete, we kind of hold them in some sort of temporary buffer before actually make their impact permanent. And we call that permanent impact retiring. Okay, so basically we are introducing a concept called retirement or commit. Some people call it commit, some people call it retire, which means that in order to make the impact of this instruction forever permanent, basically two things might happen. One is either we update our register file, or we write the results back to the memory. But if we do any of these two, we are kind of like permanently making an impact from the instruction. So when we're saying some instruction is retired, it means that we actually write back the results into some sort of a memory, either a register file or memory. And what we should do is that during the completion, we don't do that. We just write the results in some sort of a temporary buffer. When the instruction is clear to be retired, then that's when we actually do these two actions. Okay. So how do we do that? We introduce this additional buffer at the end of our pipeline, and we call it ROB or reorder buffer. Okay. So the way it works is that if you look at your processor, is very simple view of your processor would be basically three parts. An in order, fetch and decode, engine, an out of order execution engine, and then a reorder buffer. So what will happen if you remember? I said that basically our system is this CPU and this memory. And what we do is that we're gonna go and grab these instructions one by one. More. This happens. We're gonna go and grab these instructions one by one, and we go to the next one and next one. So when you're reading this, we're gonna read them in order, but then we're gonna execute them out of order. Just basically depends on which one is ready. We're gonna just move it into our execution engine. But as I said before, you might have a situation where you run this instruction before this instruction, or you run this instruction before this instruction. So what we're gonna do is that when they're completed, we're gonna put that results, whether that's value that needs to be written back to the register file, or the value that needs to be written into the memory and so on. Instead of writing it directly to the memory or writing it directly to the register file, we write it into this buffer called reorder buffer. So for example, in this example that I'm showing to you, is that let's say instruction 1, 3, 4, and 6 are completed, and we are waiting for I2 and I5. Okay. So now let's see what happens. So since I5 and everything above I5, I1 and everything above I1 is kind of finished in this buffer, we usually have an index, an indicator that shows that what is the last instruction that has been retired. Okay. We usually call it the head of the ROB, or it's like a stack pointer in some sense. Just the beginning, the last thing that has been retired. So for example, in this case, the head of the ROB, let's say, is actually pointing to this R1. So now what happens is, since this is the last one, it's safe to retire this instruction. So we're gonna retire this, remove it from our buffer. We're gonna write back the results of I1 into our either register file or memory, whatever you needed. And then we need to move our head of the ROB to the next instruction. In this case, it would be I2. But as you can see, I2 has not been completed yet because probably it's a branch instruction or depending on something else. So for some reason, it takes more time for I2 to be completed. And as you can see, I3 and I4 is already completed, right? But since I2 is not completed, we cannot, release I3 and I4. The reason for that is that if we at some point realize that, oh, I3 shouldn't have been executed, then it means that I3 and I4 also, and everything after that also shouldn't be executed, right? So we only release, or retire instructions in order format. So in that case, given that I2 hasn't arrived yet, I3 and I4 has to stay in our ROB buffer, okay? So they have to wait there until I2 arrives. We wait for some time, but just keep in mind that our out of order execution engine keeps continuing execution. So it never stops the processor from reading instructions and executing instructions. As long as we have space in this ROB, we are good to go. And usually ROB is big enough that has space for multiple of these instructions. So we keep our engine running, but we just store things here until the I2 arrives. At some point, this I2 we're gonna arrive, and then that's when we can start committing all these instructions. An alternative scenario is that when I2 arrives, and let's say I2 was a branch, and now we know that for example, we guessed that it was taken, but the correct result is actually is that correct result is it's not taken. Okay. In that case, we basically shouldn't have executed I3, I4, I5, I6, and all those things, right? So what we need to do is basically flushing. And the beauty of the ROB is that the flushing is just the simple thing of just discarding all these other instructions. So if we realize that all we need to flush, all we need to do is basically discarding all these values. So we just remove it, zeroing out our buffer, and that's all we need to do for the flush. We go back to the correct instruction, we start executing. So the only bad thing that happens is that we just run these instructions, just the execution of this instruction goes to waste. We didn't need to execute these instructions, so they are actually wasted. But nothing bad in terms of correctness happens because we never actually write back these results into our memory or on register file. And as I said, since the majority of the time we are making a correct decision, this very, very rarely happens. Okay. And that's the story of how we actually do the speculation. This happens for branch. But the important things to remember that it's not just branch that creates a speculation. For example, for memory, we do a speculation. For stores, we might have this, for load and stores, we might have speculation and all those things. Okay, so there are plenty of these advanced features these days being used in modern processors, and they all use various type of speculation in order to improve the performance. Okay, any question here? Okay. So as I said, the goodness of speculation is that there is no correctness issue. So never, because of the speculation, your program behaves incorrectly. But on the other hand, you get a significant performance boost, and that's why speculation is a standard in every single processor that these days you use at the laptop level or cell phone level. Very tiny processors still using order, but more advanced processors, all of them use the out of order. Okay, so now that we know all these tools, let's see how an adversary can exploit this. And you probably now know a little bit of what's going on. So we are talking about a performance feature like an optimization, and you probably know by this point that kind of every optimization that we have added to our computer systems, unfortunately, in the past decades or so, usually results in some sort of vulnerability for an attacker, because the attacker can also use that for their own use. So let's actually see how the transient execution attack works. So to understand how the attack works, I'm going to show you in the next slide with one example, two concepts that you need to understand. The first one, I already discussed it. So for example, when we have a branch, right, and we don't know whether this is going to be taken or not taken, we usually make a guess that say that this is going to be taken, and then we start executing the taken path of the branch. The period at which that we don't know what is the outcome of the branch until we know what the outcome of the branch is, we usually call this a speculation window or transient window. It's a temporary window that we're not sure but whether these instructions that we are executing are correct instructions or not. Okay, and this transient window basically depends on how long it takes for this branch to be resolved. And if this branch, for example, is dependent on a value that is coming from the memory, if that value is coming from the main memory, that could be thousands of cycles. Okay, so this window could be really, really large in some cases. Okay. The second thing that happens is that, as I said, during this speculation window, all we do is that we complete the instruction. We never commit these instructions. Okay. So as a result, for example, if you are accessing a memory, we never do the checks of translation and all those things. All we do is that we send a request and then we get the results back. But I mean, checking whether this is for example, belongs to this memory, or whether we can, translate this address or not only happens when we are retiring this instruction, because that's when we actually does it does matter. Okay, so we typically during the speculation we just sending requests to the main memory or to the cache and get the results back. The checks only happens when we are retiring the instructions, and that's basically the recipe for the transient execution attacks. The transient execution attacks actually have multiple different variants. The one that I'm going to discuss here is the Spectre variant and the original attacks that people have used. Okay. So what happens is that basically it's a very simple 3 steps for a transient attack. The attacker first creates a transient window. It basically means that the attacker needs to create a bunch of instructions under some sort of a branch. During that branch, a speculation window, the attacker actually accesses the secret value, the illegal value that it was not supposed to access during that period. And accessing that's gonna bring that value into the cache. So it's gonna bring that value from the main memory to the cache, because every access that we make, if it's not in the cache, we're gonna go and bring it from the main memory and we're gonna put it in the cache. So although that technically we shouldn't be allowed to access this memory, since we are doing it during the speculation, the operating system never checks whether we are allowed to do that or not. We never read that value, because reading that value will throw an error, because reading that value only happens when we are doing the check using the operating system. But just the sheer access of these secrets will cause this effect of moving data from the memory into the cache. Okay, it will be brought into the cache, and then the final steps is that we need to extract this information from the cache. And that will be used, for example, using a cache side-channel attacks that we already discussed. So that basically, this step 3 is basically going back to the victim and the attacker scenario that we discussed extensively in the past few lectures. Okay, so let me actually give you a real example. Let's say this is the victim code. Okay, and the victim code has a bunch of different arrays. And it has some sort of a secret, okay, some secret value, and the attacker is interested to, extract this secret value, okay? So what will happen is that there is some sort of a vulnerability, some sort of a victim function that has a behaviors like this, that it has a branch, and in that branch it's basically accessing, another array, okay? So it's like basically, based on this array size, and this value, this input value that's coming from an outside, is basically access another part of the memory. So what does the attacker do? The attacker basically does this. That it's the attacker, since this value is actually being written, being read from the outside. The attacker plays with this X value. The attacker first, what it does is train the branch predictor to always think that this is, for example, a taken branch. So for example, always send X's, X1, X2, X3 for some period of time. Always, all of them are smaller than the array size 1. Okay, so this basically means that the branch predictor expect that majority of the time this X would be below some threshold, which means that the branch will be the if statement is true. So what will happen is that the next time that we send another X, the branch predictor thinks that this should be probably also be taken. So the guessing part or the speculation part would be taken. Okay. So now that the branch is taken, the attacker actually now knows that this instruction is always almost guaranteed that's going to be executed during the speculation. All right. So now what the attacker does is that using this trick of sending X this time that is much bigger than the array size. Okay. And given that it's much bigger than the array size, it actually does not really access the array size, that the actual, the array that we're thinking about was actually accessing somewhere outside this supposedly array size, somewhere here. And the attacker can actually use a bunch of different techniques that we're not going to discuss to save some time in order to basically finding where this secret is. And just by changing this X, is actually accessing this another memory line and brings that data to the cache. Okay? And then basically using a simple cache side channel attacks, the attacker managed to extract that value from the system. So to just repeat again, basically the attacker plays with this X value, and all it does is changing this X value at the beginning. It's kind of like train the system and thinks that okay, its values always will be less than the array size. And in that way, the branch predictor is kind of trained and expect that this value will be always less than some threshold. Then during the actual attack, what the adversary does is that it's going to send an X that is much, much bigger than what it's supposed to be, much, much bigger than the actual array size, which means that eventually what will happen is that the adversary is going to access some other part of the memory that it shouldn't supposed to access. So it was supposed to access only here, but it's actually accessing some outside part of this memory address. And this way we basically, there are some additional complexity that I intentionally skip, but generally at the end of the day, what this gives the attacker this possibility of reading basically virtually anywhere in the memory that he or she wants. And this way he can bring data to the cache and then use more clever cache side-channel attacks to actually extract this information for its own uses. Okay, so that's kind of like the gist of how the speculation, transient execution attack works. The details really depends on the variance. For example, how exactly you find that address, how to bring it in the cache, what would happen after that, and so on. But the only thing that I want you guys to understand from this slide and generally from this part of the lecture is that transient execution attacks happens just because that we are, accessing the memory during a speculation, and then during that access, we can actually access technically anywhere in the memory, although we're supposed to access only portion of the memory. Okay. And this will bring the data to the cache, and then we can launch cache side channels attacks and all those other attacks that we discuss in the course to actually then finally extract the value that we want. Okay? Any questions? Cool. If you're interested to know more, I'll definitely suggest you to check out the Spectre paper. It's easy to read, so we can very quickly figure out what's going on. But yeah, so as I said, I'm intentionally just skipping some of the important details about this. So if you're interested, go and check it out. So one thing to understand is that this idea has been presented about like 3-4 years ago. And since then, there are lots of other variants of this and types of different ways of exploiting this. So, branch and branch miscalculation is only one scenario. There are many other scenarios where the attacker can actually create some sort of a speculation, and using that, the attacker can basically, extract information. Okay. So, there's these days there's a huge body of work of showing that, okay, by the way, you can, for example, exploit this and exploit that. You can exploit, exceptions. You can exploit, interrupt handlers and all those things. So it's not only limited to the branches or this specific scenario that I mentioned, but all of these are basically, kind of exploiting this bug in the system that during a speculation, we don't do some of the checks that we normally do when we are doing during the retirements, and that's the main reason that this issue happens. Okay. So and then you might wonder what should we do to defeat these attacks. This is also a very active area of research. The short answer is that there is no easy fix because this is just fundamentally how the processor operates. The speculation is one of the fundamental part of the processor. Of course, the straightforward fix is that you disable speculation for some time, or if you have like a secret value at some point of your program, maybe you disable the speculation here and enable it here. So there is instructions like fence that you kind of like, avoid and prevent your system to reorder instructions during that period. So that's one thing that can be done. Basically, you are temporarily, eliminate the effect of this vector meltdown type of, transient execution attacks. But that requires lots of manual work because you need to go through every part of your program, know which part you need to be worried about, and so on and so forth. So the more hardware-oriented solutions is actually what people are thinking about. There are various, as I said, various different solutions. Most of them are basically, trying to prevent some sort of, moving information to the cache or randomizing the cache or detecting this sort of, behavior, this sort of gadgets in the program and then trying to eliminate this. There are various ways of detecting this. But generally, the fundamental idea is that we need to protect the data during this speculation, okay? And we need to either, change the design such that, the data is not brought to the cache, or if it's brought to the cache, maybe it goes into some private space and then go back to the cache and so on and so forth. These are generally, the solutions that I just described, temporary, disabling the speculation, detecting this sort of vulnerabilities in your code, or adding some sort of a hardware support to your system such that it can, for example, prevent this. Okay. Any questions? These are some key takeaways from you guys. Read it on your own time, but generally, what this transient execution attack says is that the isolation assumption that we had, unfortunately, because of such speculation, can be circumvented. And combination of transient execution attacks and side channels attacks can be very deadly and can extract technically any information from anywhere in the hardware, anywhere in the memory. Okay. So if we are successful with the transient execution attacks and combine it with the actual cache side channel attacks, for example, then you're virtually able to read even the kernel information from your processor and all those things that exist into your memory. Okay. And then generally takeaways from the digital part before we move on to the physical part is that shared resources is the fundamental issue for digital side channels. And it's not something that we can prevent because the computers that we have these days, in order to improve the performance, we need to have lots of parallelisms, lots of sharing between multiple threads and so on and so forth. We cannot afford to say, okay, every computer that we have only runs one process at a time, and that's it. So that's not how it's going to work because building large processors is very cheap, and then what you can do is that having the multi-core with 8-core, 16 threads, and so on. So you basically have the potential of running, for example, 16 threads at the same time, and this will result in an opportunity for an attacker where one of these 16 threads becomes an adversarial, process or adversarial mean for attacking the system. And there are all sorts of different ways that the attacker can use these resources in order to extract the information that he or she needs. Okay. Any questions about digital side channels in general or transient execution attacks? Cool. So now let's shift gear and focus on physical attacks. So the first thing to understand is what is the major difference between physical and digital? There are three main things that you need to pay attention to. First of all, the physical, as the name suggests, requires some physical proximity to the device. So it's not like, you can launch this attack 1,000, miles away from the device. In order to, extract the physical characteristics of the system, you need to be close to the device. How close depends on what type of, channel are you using, what type of signal are you using, what device are you trying to attack, and what sort of equipment that you have. But you're usually talking about few meters distance, okay? So you need to be actually, be physically present in the same room with the device that you're trying to attack, okay? That means that, the applicability of physical attacks is completely different from the digital, because digital is, as I said, technically from anywhere you can launch an attack, for example, into Amazon Web Services or Microsoft Azure or so on. But for physical, you need to actually be in the same room with the device, okay? So that's number one. And because of this, basically, the measurement tools or the setup for the physical attacks is different from the digital. From the digital, all you need to basically is creating a process, right? So you need an adversarial process to get into the system. Versus for physical, what we need to do is having an actual equipment for measuring the signal. Depending on what you're measuring, since you're measuring an actual physical signal, you need sensors, right? And you need, measurement equipment. For example, if you want to measure the temperature, you probably need a temperature sensor, and then you need some sort of a device to stream this data to that. So, for example, you need an oscilloscope, or you might need a digitizer or something like that in order to read that information. In order to measure electromagnetic side channels, you probably need some sort of an antenna or a probe. You need something like a spectrum analyzer or an oscilloscope. So you actually need physical devices, okay? But the most interesting things about the physical versus digital is this concept of what's called an air gap, okay? So air gap is actually, given that, the challenges that, connecting your computer to the network can bring. So if you have a computer here, of course, if you connect it to the network and to the internet, what will happen is that you're basically opening the door for all sorts of attacks. As long as your computer can be seen in the internet, it means that virtually anybody in the world can access that computer, can at least interact with that computer, okay? And while for all the consumer-grade devices, including our laptops or cell phone and so on, this is what we want because we want to have access to the internet. For more security-sensitive applications, such as governments or specific, industry or scenarios that is, the security is the utmost, priority, we usually have what's called an air gap, which we never actually connect the computer device directly to the internet. What we do is that we either have some sort of a local connection between multiple computers, and then maybe have another computer as the gateway, and then we only connect this to the internet, okay? So basically accessing any of these internal devices inside this local network requires to access and attacking this gateway. And then you can have a bunch of different, security features and measures in order to make sure that this gateway no way can be attacked, okay? And that's why these devices are basically what's technically called what's called air gap, because they're not, connected directly to the internet. So all these techniques that they mentioned that, you can, do ROP or buffer overflow and et cetera, kind of doesn't work on these devices because they're not actually, there's no way of, infiltrating into these devices, okay? And so all these ideas about, remote attacks kind of like, gone. But interestingly, still the physical attacks are possible because physical attacks has nothing to do with the way that the computer operates and interacts with the outside world. It's just the physical characteristics of the device. So as long as you can, go inside the system, be physically present here, and then you can collect this information. So physical attacks actually have this important aspect, an important feature that they can operate even under air gap systems, and they can actually extract information from the air gap system as well. And that's the major difference between physical and digital. And that's why, physical is also equally important as the digital side. All right? Any questions? So what is the goal in physical side channel attacks? Goals are very, very similar to digital. So typically what we are looking for is extracting some sort of value from the system. And these values are usually sensitive values. The majority of work in physical side channels attacks has been focused on how we can extract the keys. Because as you know, extracting keys just using a normal software level is not possible. We extensively talk about how these systems are proven to be secure against brute force attacks and all sorts of software attacks. But what the attacker can do is basically, using the physical characteristics to understand what is the value of the key. So for example, let's say I measure the power, and whenever I, XOR, for example, my value, so let's say my X with key, if the key is equal to 1, I get like a behavior like this, if key is 1. And if its key is 0, I get a behavior, like this. Basically, the amplitude is significantly lower, for example. So what will happen is that if I manage to measure the power consumption of this device, and being able to measure this XOR, this functional activities bit by bit, very easily I can tell that whether the bit was equal to 1 or whether the bit was equal to 0. And that's going to be the way that an attacker is going to analyze the signals in order to extract this information. Okay? And later on, we're going to also discuss that this could be a nice way of exfiltrating data from an air-gapped system. Generally, the counterpart of what we discussed as a covert channel communication in digital side channels, that could happen with the physical side channel attacks as well. Okay? So now let's actually go a little bit deeper and see how the physical side channel attack works. So generally, you can define the problem of attacking a system using physical side channel as a problem of we have two variables, basically three variables. We have the input x, we have the f of x, the results, and then we have basically what we get from the physical side channel attack is we have this signal. For example, for the cryptography, what we have is we have f of x, right? We can just query we can query a system and get the f of x. We can query the system and get the f of x. We don't know what x is, right? And we said that if we can break the system and get the key, then obviously we have the answer. But we already proved that that's not possible. But with side channel attacks, not only we get the f of x, but we get the signal of f of x. What is that signal? That depends on what we are collecting. Let's say, for example, we are measuring the power consumption of this device. So we not only, we see the actual results, but we also see the pattern of which that result is being created. So let's say, for example, it takes 1 millisecond for AES to encrypt something. What we're going to get is that we're going to get the results of the encryption, and we're also going to get 1 millisecond worth of analog signals. Okay? And what we want to get from this is being able to detect what the key was, being able to predict what the key was. And this is basically, since this is the signal that we're getting, we're talking about an analog domain signal. This basically extracting information from this in order to find what X is becoming some sort of a digital signal processing, or in these days, it's a machine learning problem in some sense, because you have this time series signal, and you want to extract what is the value that created this. So it becomes some sort of a classification problem in some sense, that you have a bunch of different signals, and you want to say what is the X for this, what is the X for this, and what is the X for this. Okay. So physical side channel is basically the problem of solving the physical side channels is very, very relevant to state-of-the-art digital signal processing problems and or machine learning problems, because all of them are also trying to solve the same problem. The only thing is that the source of this signal in this case is an embedded device, it's an IoT device, it's a computer, versus, for example, in speech processing, the source is a human voice, right? So that's the fundamental difference. But the class of problems is very similar. So that's why you will see that, majority of our work in this domain is trying to, use and apply those similar techniques into the same signal. Okay? To give you a little bit of history of why and how physical side channel attacks becomes interesting, it's actually the story of like just a little bit after World War II, where U.S. intelligence actually found that some of these equipments that they use in the military actually create this emanations, this signals, that if you record it and analyze it, you can actually understand what the original value was. And this, for example, could be used for if two, people are communicating with each other. What they found was basically that by just looking at the signal, although the signal itself is encrypted, so you can never understand what the signal is, but you can understand what the message was. And that's kind of breaks all the assumptions that we had about the crypto system. This was like a secret program in U.S. intelligence called, Tempest. It's a stand for, I don't remember right now, but it has something to do with, emanations and yeah, actually, I think it's here. Anyway, so the Tempest program becomes the gold standard afterwards. So now it's actually, a non-classified program, and what is the requirement for all the devices? And basically, what this says is that every device that we're going to use for security purposes has to follow some specific protocols and has to pass some specific tests in order to make sure that this device is not revealing secrets about the actual information inside. So this is actually widespread these days, and everybody's kind of using it these days. To give you a little bit more of a history, is actually the evolvement of the story around physical side channels evolved throughout decades. And basically, the trend is as we use more and more of these electronic devices, bigger and bigger electronic devices, and more number of these devices, basically the physical side channels becomes a more and more problem. So, for example, what happened was during 90s when we start using credit cards, people showed that the actual secret values that are stored in a credit card can be easily read by some sort of a power side channel. So as long as you get access to someone else's credit card, you can launch a very simple attack in order to get the values, and then basically you can replicate that credit card. And at that time, that was a huge, problem, because then the entire security and integrity of the credit card was in question. Another thing that happened was another large part of this physical side channel was key logging. So there are large part of these in the literature shows that, for example, if you type something, because of the physical characteristics of typing, it could be the sound, it could be the way that you type, it could be the signal that is generated by the way you're typing. An adversary that is near to you can actually record what you have typed and then use that in order to understand what you're doing. So, for example, a very famous one is this coffee shop attacks, where you sitting on your desk maybe on Starbucks and then typing on something, maybe like paying something online or doing something, and someone else in the same coffee shop is sitting somewhere here, and then just by listening to the sound of your keyboard can understand what you're typing and find the numbers that you have typed. Okay. And then simply basically just figuring out what exactly you have typed. This could be even more sophisticated and ask you, for example, oh, click on this link and then maybe write down your name or password and so on. And once you're doing that, you're listening to it, and then it can actually reverse engineer that. There are many of these examples, but just generally the idea is that because of these physical characteristics, if somebody gets close to you, and unfortunately this is the scenario these days that happens more often, an attacker can actually record this information and launch a side channel attack on your proprietary or your secret information. Okay? Any questions about this? All right, so going back to the problem that I mentioned. So basically, as I said, the problem of physical side channels attacks becoming a signal analysis problem in some sense. What we usually assume is that similar to encryption and crypto systems, we assume that the way that we are creating this f of x is known. So we not only get the f of x, but we also get the code or the function that creates this f of x. Okay, we actually know, for example, the f of x is this sequence of instructions. For example, an easy example is AES. So your f of x is basically AES. Okay. And what you're trying to access, your x in this key is your secret key. So you want to extract this secret key. You know how the f of x works. You get the signal, you get the output. So now the question is that having all these information, how can I extract the secret key? Okay. So there are three models or modes that we can actually launch an attack. They call simple side channel attacks or SCA. Then there is another one called DPA or differential power analysis or differential EM analysis, DA. And then there's the last one is called template based. And then we're gonna, in the next few slides, I'm gonna talk about the difference between these. The simple one was, as the name suggests, the simplest method for doing this. It was the very first, method that's used this, especially during the credit card analysis time. This was the attack that is used. Once people get more and more educated and informed about the potential, attacks and scenarios that can happen for simple analysis, they actually designed their system to be robust against simple analysis. And that's when the differential analysis can come into the play. We're going to discuss what differential analysis is. But again, once the differential analysis also gets widespread, the systems, especially in more modern systems that is designed during early 2000, also they are robust against differential power analysis. And these days, what we're using is what's called a template analysis that usually use some sort of a replica of the device and using machine learning these days, for the most part, in order to attack the system. And that's where we are right now. Again, similar to any other concept that we discuss in this course, attacks and defenses against physical side channels is also an arms race. We design systems to be robust against them, but the attacker also gets more and more sophisticated. Okay? So before we jumping in, let's have a quick break, and then I'm going to discuss these three different types of attacking using physical side channels. Right? All right, so continuing on. So now let's talk about these three different methods for physical attacks. The first one is, as I said, the name suggests, is simple analysis or SA or SCA. What SA does is it's just a very simple analysis, which usually is just some sort of a visual or signal examination. Okay. So, for example, if I give you an example, this is like an actual signal that I personally collected from a microcontroller very similar to Raspberry Pi. And what it does is basically I'm just collecting the ping signal. Okay, so I'm pinging, I think, Google website. And you see that, and then I'm collecting the electromagnetic emanations off of this device. And this is the signal that I'm getting actually. And you can clearly see that very distinguished, kind of like, pattern and phases. For example, I can see that this is the packet creation, this is the request response, this is the delay calculation, and so on and so forth. I can actually, analyze my pin code, and then I can actually, just one-on-one map this to the actual activity. Okay. And for example, I can see how much delay it takes for packet creation, how much delay it takes for response. And one thing that people have shown with this simple analysis is that, for example, they can find the location just based on this. How long does it take? Another thing that people have shown was what's called website fingerprinting. So let's say I access Wikipedia, I access, oops. I access Wikipedia, Google, many different websites, and then I just kind of collect these the signal for all of them. What I can tell then is that the next time I'm accessing any of these websites, I can just look at this pattern and say, okay, which website I have access to. And just again, going back to the coffee shop attacker, the coffee shop attacker or hacker can just sit there and collecting the signals from your system and just tell which website you're using. And I mean, if you're interested, there are attacks that shows that how this could be, amplified and becomes more serious. Like, starting from just knowing what website you're visiting compared to which link are you clicking on that website, how much time you're spending on that website, et cetera, et cetera. Okay. And this simple analysis was mainly, as I said, used in the past specifically for credit cards, because people saw that it's actually, the actual activity of the credit card was like very simple, activities that you can clearly see zeros and ones once it does for example, the authentication. And that was a huge problem at that time because, as I said, the entire integrity of the credit card is kind of like, went into question. Okay. So the basic, challenge with the simple analysis is that, of course, if you know that, your program is very obviously can be seen and can be detected using these phases, you can come up with scenarios and changes in the software so that, it's not no more obvious. You add some randomness, you add some sort of, unexpected behavior, you add some additional activity so that, all these phases kind of look similar, at least visually similar, okay? And another thing is that, for some cases like this, you can actually see the difference between phases. But if you, for example, zoom in here, during the packet creation, you cannot really see much difference, right? So it's not like, every activity that you do has this very different signatures that you can very easily, detect. Simple analysis can kind of give you some sort of an overview, but doesn't mean that it can actually, solve all the problems of the adversary, and the adversary can basically find anything that he wants. All right. So that's the two main challenges. And in order to fix these challenges, the idea was, okay, how about we look at the differential behavior of the system? And that's what's called a differential analysis, okay? So the differential analysis has 3 steps. The first step is, okay, at the end of the day, what we want to know is X, right? So remember, for example, we want to know whether this was bit 0 or bit 1. Let's say for now, the X is only a binary value. What we do is that we are saying that, okay, I have a bunch of different samples. And what I'm going to do is that I'm going to make a guess for each of these. I'm going to say, for some reason, these samples are coming from X equal to 0. And these samples are coming from X equal to 1. Okay? Then what I'm going to do is that I'm going to average all these and average all these. And I'm going to differentiate these two from each other. So we're going to subtract this signal from each other. And if indeed this was a correct way of classifying these two, I should see a spike or a big difference between these two. If I just made a mistake and used a wrong condition on classifying this, basically what would happen is I had randomly, sampled these into 2 groups, right? So let's say that the reason that I thought that these are X1 and X2, X0 or X1 are completely incorrect. And in that case, the way that I classified or categorized this was just some very random, reason, right? And in that case, both groups has very random behaviors, and the average of those random behaviors subtracted from each other would be 0, because we are subtracting a random behavior from a random behavior, and technically we're going to get something close to 0. Okay, so that's the idea, that if you make a correct decision about X, then we will see a significant difference between these two groups. If we don't see any sort of meaningful difference, it means that the criteria that we used for classifying these two was incorrect, and then we have to go back and classify it again using another criteria. So this way, although that, by just visually looking at these different samples, I cannot say which one is X0 or which one is X1, but if I categorize them correctly and then average them together and then differentiate them from each other, then I can quickly find what is the difference. And of course, the assumption here is that there is a difference in signal when you're using X equal to 0 versus when you're using X equal to 1. Okay, if there is no difference at all, then regardless of how do you categorize these two, you'll never see any difference. Okay, so the beginning assumption is that if I do X equal to 0 and create the signal versus if I do X equal to 1 and create the signal, there will be some difference. That difference is not obvious with simple analysis. So maybe I can use this more advanced scenario. So basically, differential analysis giving you two things that simple analysis doesn't. One is the averaging behavior, and the second thing is kind of like, going with a hypothesis that you don't know what the answer, whether that answer, the hypothesis is true or not, but you know the answer when you see it, basically, right? If you see the big difference, it means that you correctly, classify these two from each other. Okay. This is kind of, one way of using this in AES actually. So this was originally was designed for AES. There are some subtleties and additional details that you need to pay attention to. That, I mean, if you're interested, go and take a look at this reference. But generally, the idea is that, we have a chip, we use, for example, power EM traces. We make some assumption about the key. Based off that, we classify the signals into two groups. And if if the assumption was correct, then we will see a peak like this. If the assumption is not, then we are kind of like, just subtracting two random behavior from each other. So we will see something like this. And this way you can know whether the assumption about the key was correct or not. So if I see this, it means that this assumption was correct, which means that I can find the key. If I see this, it means that the assumption that it has about the key was incorrect. So I move to another possible scenario. So it basically becomes some sort of a brute force, but the brute force is much more guided compared to when you just do a simple brute force, right? Because you see the difference this way versus the way that we just run the brute force and try to find the entire key. Does that make sense? So as I said, the difference between the DA, the differential analysis, and simple analysis is that simple analysis usually is just good for when you can visually see the differences. But because of the noise or because of the complexity, differential analysis would be a superior option. And usually what happens is that you typically use both of them in order to attack. So if you go back, for example, to this scenario here, what you can do is that saying that, okay, using simple analysis, I can at least find this different, phases. And then what I can do is that, for example, if I want to see the response or analyze the response, then I can launch some sort of a differential analysis attacks in this part of the execution. Okay, but typically, you see a combination of differential analysis and simple analysis. Okay, but both of these are kind of like solved problems in some sense. So because the attack, the defense mechanism, these are kind of like very established type of side channels attacks, and has been around for quite some time. So that the people have finally realized that, you know what, we have to, make our system robust against them. And that's why these days, the third category of side channel attacks is really the one that you have to be worried about. It's being used extensively. And that's what's called a template analysis or template attacks. So the idea of the template is we want to create some sort of a template, some sort of a dictionary about behaviors that we see. And we use that during some sort of what's called a training phase. So during the training phase, we start creating all these templates or all these dictionary entries. And then during the attack, what we're doing is some sort of a pattern matching between these words, these entries that we have and the signal that we receive. How do we do that? We follow this kind of like three-step algorithm. The very first step is that we're going to say that we have access to a replica of the device that we can attack. And this is not unrealistic because then, for example, if somebody wants to attack this MacBook Air, you can easily go and buy another MacBook Air because usually all these devices have plenty, right? So you can always get your hands into some sort of a replica to that device. Doesn't have to be exact replica, but even some sort of hardware that is shared among the two should be sufficient, right? So you get that, and then what you do is that you start your training phase. The training phase is basically saying that, okay, if I want to like find x from f of x, what I can do is basically runs this huge set of x1, fx1. I can create this large set of x1, f1, x2, f of x2, and so on, right? And nothing prevents me from, running a large set of these, x1, fx1 pairs, because I'm the attacker. I have the access to the replica. What I would do is that I know what x1 is. I use that x1 and feed it to f, and then I get fx1, and then I'll also get, signal 1. I get signal 2, and so on and so forth. Okay? So I have all the three things that I want. I have the f of x, I have the x, and I have the signal. And this would be basically what's called the training phase. I create this templates of all these different behaviors that I want to have. Then what will happen is that we build a model off of this. So I build a model based on this training data. And now I have a trained model. This model doesn't have to be necessarily a machine learning model, but I mean, this is kind of basically the recipe of a machine learning system. But generally, any model using any sort of algorithm that you want to use, we will train this model here. And now it's time for the attack itself. During the attack, what you should do is you basically you get the f of test. Basically, this is f of x that we don't know, right? So you don't know what x is. And what you would do is that you start comparing this f test with all these, replica that you have here. And using some distance metrics, some similarity metric, you will, for example, say that, oh, this looks very similar to this third option. And then you go and check what is the value of x for this third option, because you have the pair of x and f of x. And then it basically means that this x is equal to this x. And that's how you're going to find the x. Basically, you're building your model with this large dictionary, and then during the attack, you basically compare that signal with your large dictionary. And once you find that, you basically have okay. So kind of like here, I'm showing you an example. What you're seeing here is this is the f of test. This is again, these are real signals, and this is the training signals that I created during the training. Let's say that this is the signal for a branch taken and not taken. So let's say we're doing branch x, and if the x, for example, is bigger than 0, then this branch is taken. if x is equal to 0, then the branch is not taken, right? So, and then I'm getting this signal and I want to know whether x was equal to 0 or was not equal to 0, whether this branch was taken or not taken. So what I do is that I run this with multiple different x's and I collect all these signals here. So for example, I'm showing 2 signals for the taken branch and 2 signals for the not taken branch. And then what I'm going to do is that I'm going to compare this signal here with all of these 4 options, this one, this one, this one, and this one. And I'm going to use a metric. For example, in this case, I'm using correlation, which is basically, you have 2 time series. You can just always calculate the correlation of these 2. And then I'm going to just, report the results. And what I'm seeing here is that, for example, there is a 0.92, the correlation value of comparing this signal with this. There is 0.79, 0.13, 0.16. So if I compare these 2, is that more than likely this is the signal this is the outcome that I was thinking, which means that basically this branch was taken, which means that the x was not equal to 0. Okay, so that was kind of like what we want. So we see this, it's not obvious which one of these is actually matching with this. But if we have a large set of training, and then if you use a right distance metric, then we can basically, again, correlate this back into the original data that we're using. And now instead of x, now think about that, this is basically becomes the key. And now what we want to do is that based off the key, remember we had the RSA thing, and then we had this, based off the key, we do this some sort of activities, right? And during the task side channels, I told you that. Basically, this is one way of finding that x, but just looking at the branch pattern and then trying to see that whether the branch was taken or not. Okay. Any questions? Can we just fix the 10 down? Okay. So that's the story of template analysis, but there are a bunch of questions that we need to answer, right? So for example, what is the right metric for comparing these signals from each other? The answer to that is unfortunately, there's no like one right answer. It really depends on what sort of application that you're using. Correlation, for example, is one of the main and most widely used type of metrics. Machine learning in general, so instead of like actually comparing 2 signals and using some sort of a signal processing metric, what you can do is basically you can train your system using machine learning. So for example, I'm using a CNN, a convolutional neural network. And what I'm going to do is that I'm going to basically have a list of labels of x and f of x. And I'm going to feed the signal into this machine. And I'm going to label it with x1, x2, x3, and so on. Okay? And then I'm going to train this machine learning model, the CNN. And then during the attack, what I do is that I have the CNN, I feed the signal to it, and then that's going to give us a classification of whether this is x1, x2, x3, and so on. So very similar to the way that we do, for example, image recognition. What we can do is also doing this type of attacks, this type of side channels attacks on our CNN as well. Okay. And then another thing that you can use more sophisticated metrics such as similarity metrics, cosine, similarity, F2 distance. These are just, if you're into signal processing, you probably know these better. But generally, as I said, at some point this becomes a sophisticated signal processing problem. And what you want to do is being able to, optimize this problem. We're not going to go through more details of that, but if you guys are interested, that's an interesting problem always to look at this in more detail, right? Another things that you need to pay attention to is that you have different options for the signal analysis itself. So for example, what I'm showing here could be a time domain signal, because remember, we're having a sensor, for example, an antenna, and you have a measurement equipment, and then what you're doing is collecting the signal and then do the analysis. You don't necessarily need to do this analysis in the time domain. You can do it in the frequency domain. You can even, transfer it in some intermediate domain. You can do wavelet analysis, for example, on the signals and all those things. Okay. So the analysis of the signal also becomes an interesting and important challenge. And again, similar to different, different signal processing problems, this is also an interesting problem that you can take a look at. Okay. For example, the frequency problem, the difference between the frequency and time domain is that frequency domain gives you some sort of an average behavior of the signal. So in some cases, that could be very useful to reduce the transient noise and so on and so forth, right? On the other hand, time domain is probably giving you a better resolution in terms of what is going on at each clock cycle and so on. So in some cases, we might be interested to look at it that way, okay? And then another important thing for the signal analysis is that, again, similar to other signal processing problems, there is usually some sort of a pre-processing phase, dimensionality reduction, noise removal, normalization, regularization, and all those things that you usually do for other signal processing problems, such as speech processing. That's also usually very important and very required for physical side-channel attacks as well. Okay. So these are some of the examples. For example, alignment or synchronization is another big thing. Remember, for example, for differential analysis, we had to, average all this together and then do the differentiation. So synchronization is a key thing to do for these scenarios, right? So we need all the samples to be synchronized before we actually do any sort of averaging, right? So all of these problems, again, going back to what I said originally, I'm repeating it over and over. At some point, this becomes more of a signal processing issue rather than anything else. And you have to pay attention to all those challenges. And then the kind of like final thing about the template analysis is that although we say that you can get a replica, a physical replica of the device that we want to look at, in reality, what happens is, from one device to another device, there is some sort of variation. The variation is small, but there exists a small variation. So it's not like, if I run the same x and f of x in two different devices, x0 and f of x1, x2 and f of x1. If I run it on, if I run this on two different devices, the signal that I'm getting might be slightly different. So it's not like we're getting exactly the same thing. It depends on the signal that we are looking at, the sampling rate that we are looking at, and all those things. There is a small variation, and we have to be able to kind of tolerate that variation if we want to get good results. Okay. There's also environmental variations such as temperature or runtime. So for example, if the device gets hotter, the signal that we are receiving might be different than the signal that you're receiving in the normal scenarios and so on. There could be interference from the outside, right? So for example, if you're trying to collect electromagnetic emanations, there are interference that coming from the other RF signals in the same band and so on. So that's also another challenge that we have to look at. And of course, the SNR or the sampling rate of the device, the acquisition device that we use, also plays an important role in your system. Okay. So now that we know that there's these different types of attacks, then there's a question of what are the differences between different types of physical side channel attacks. Generally, the only difference is that the channel that you're using. So if you're using electromagnetics versus power versus acoustic versus RF and so on. So generally, the idea here is you can use different different channels, whether that channels is power or electromagnetics. And in all those cases, you can apply all of those things that we mentioned. the simple analysis, the differential analysis, and the template analysis. Okay. So all of those things are basically the same for all of them. The only thing is that the channel that you're receiving your information, the signal that you're receiving, is slightly different from one to another. Okay. Or another area of research these days is actually creating a new channel. So we always thought that, oh, there is only electromagnetics, but people have shown, for example, recently that electromagnetics can combine with acoustic, electromagnetics can combine with power, electromagnetics can combine with other RF signals, and so on. So it's actually very interesting these days that people have shown various different new channels that we never thought about. And these new channels actually have much more better capabilities compared to the previous channels. So that's kind of it. And the difference between them is depending on each of these channels that you're using, then the kind of like distance that we can measure these things are different. So for example, acoustic is usually very weak physical side channel signal. And it might have some useful information about your system, but usually, for example, using electromagnetic versus acoustic is a better choice. RF is usually much more stronger than both of them. So it really depends on the capability of the attacker and kind of the threat model that we need to be worried about. Okay. And as I said, there are some new side channels. I'm going to skip the details of this. You don't need to know about this, but generally, one thing to know about is that these things that I listed in the previous slide is not the only way of attacking these systems. There are other side channels, including like LoRa or RF and so on, that can actually be used for attacking physical attacks. Okay. Any questions so far? So now let's talk about the defenses and then kind of like finish the lecture. So given that, so we already discussed that physical attacks are much harder to launch compared to digital attacks because you need physical proximity to the device, right? But on the other hand, since physical attacks created because of the physical characteristics of the system, defending against physical attacks is also much more difficult because we're talking about the physics of the device. And it's not something that you can say, oh, I'm creating air gap, or I'm not letting other users see my memory content and I'm good to go. We're talking about that because of the switching, for example, there is an electric emanation. Or because of the switching, there's a change in power. Or because of the movement of some parts, there's some acoustic signals. Or because the temperature goes up, there is a temperature side channel. So it's hard to change the physics of the system usually, right? And you cannot really limit or eliminate specific physical characteristics. Okay, so defending against them is fundamentally different. You cannot eliminate them as the way that you could have eliminated, for example, digital sections. Remember, for example, I said one popular ways of eliminating transient execution attacks is temporarily, disabling out of order execution, right? So you can have like a disable here and enable here, and this way we kind of, at least at this window, that you don't have any transient execution vulnerability. There is no such thing for physical side channels because you cannot say, oh, at this point don't generate power consumption, for example, right? So what should we do is there are multiple different ways. The first way that's very popular is at the software level or the compiler level. Remember, the reason that we are seeing these physical side channels is that because we're fundamentally running different things, right? So if this is from x0 and this is from x1, if I run exact same things on both of these scenarios, then this, although I get the signal I'm getting is exactly similar, right? So if you do exact same thing, you will get exact same signal. So what you can do is some sort of creating a pattern that regardless of what your value is, you always run the same, type of instructions or same at least sequence of instructions, or at least same number of instructions, okay? Similar to basically, if you remember, we talked about cache side channels, and we said that there's generally you can do the same thing over there as well. So the idea here is that maybe when you're writing your program, maybe when you're writing your RSA program, if you have an if then else, maybe what you can do is that whatever you do, either if or else, you always run the same set of instructions. Okay. And this means that either one of them has to have some dummy instructions. So for example, if the if instruction has 4 instructions, normally your else would have, for example, 2 instructions. In order to make these two similar to each other, I need to add dummy instructions into my else branch as well, right? And this means that it's going to be additional overhead to the system, because originally, if I take in the else branch, I would have only executed 2 instructions, and now I'm running 4 instructions. So it's kind of like 50% overhead in this specific example. But at least it doesn't reveal anything in terms of physical side-channels, because regardless of whether I'm taking the if branch or else branch, I'm always running the exact same code. Okay. And how do we do that? We either, as the developer, needs to go through our program and be aware of the scenario like this, or we can ask the compiler to automatically scan the code for us and then add these additional instructions into our if then else branches. Okay. So that's one way of fixing this issue. Another way is actual physical, fix that we can make to the system. So I said that it's not easy to eliminate these signals, but there are ways to make these signals very weak. Okay, how do we do that? For example, it's very known that electromagnetic signals doesn't go past metal surfaces, right? So there's this known technology called Faraday cage that if you have like a complete metal enclosure around your device, then there won't be any electromagnetic signals coming off of that enclosure. This is usually called Faraday cage, and many of these military systems, many sensitive systems, are actually using some sort of a Faraday cage in order to significantly, reduce the amount of emanations. You can do the same thing, for example, for your power. If you limit the amount of pins, the output pins that are coming from your chip, or you kind of like make this make the access to these chips very, very difficult to the user, then the chances that the attacker can actually run some sort of a power side channels attached to your system is very, very low. Okay. So generally, this class of defenses talks about how we can make it much more difficult for the attacker to access these physical signals in general. Okay. The second category of defenses is just adding randomness. Again, the reason that we said that we have SX1 and X2 and then this different signal was that there was some correlation between the signal and this value, right? So if we can find somehow to decorrelate this relationship, so that whenever we do X1 or X2, we just do some random behavior on top of the actual behavior. This way, the attacker never understands which one of these two is actually the case, right? Because what the adversary will see is always some sort of a random behavior that regardless of what the input is, that's the signal that they get. Again, similar to the software compiler method, that can be happened using the compiler, or it could happen even at the hardware level. So the hardware can also add some sort of a randomness to your system as well. So you can have an actual hardware module that creates this randomness for you. Okay. So for example, randomly change the voltage levels, randomly change the frequency, and all those things. So this could be the source of the randomness. Another thing that can happen is, again, going back to just eliminating the signal. You may not have an enclosure, or you may not be able to add this change. But since I said that physical side channels require physical proximity, what you can do is that just making sure that nobody accesses to your system. This is basically similar to the way that the banks are secure, right? You just don't let people in and that's near the the actual the safe safe box or the valuables that you're storing in your bank. Similar story can happen for computers as well, right? So if you have a secure things stored in the computer, think about it as a piece of jewelry that you need to protect. Put it in some sort of a safe, make sure that nobody accesses it, including except the people you trust, and so on and so forth. This works for very sensitive scenarios, but when we are talking about our smartwatch and our laptop and so on, that wouldn't meet it. What you can do is, for example, if you're in a coffee shop, maybe don't type your social security number in a coffee shop, right? So you can be a little bit more aware of these potential attacks and try to at least limit amount of interaction with sensitive data that you have in public places. That could be one thing that you can do in order to kind of like make yourself more secure against these possibilities. All right, so that's kind of a story with physical side channels attacks. It talks about different types. We talked about how we can actually launch the attack. We talked about challenges, and we talked about defenses. Any questions here? Cool. So final thing before I let you guys go is, as I said at the beginning, another use case for physical side channels are for creating covert channels. Remember, covert channel was the scenario where you had two different, users. For digital side channels, we said that these are two different processors, right? And the processor, this one, for example, has access to the camera. This one has access to the network. And this one kind of like, use this information to send it out to the network, right? So in physical scenario, the idea is that you have a device, and this device is air gapped. So it's basically, there is no connection to the outside world. Okay, so this connection is kind of blocked. So there is no internet activity. And then also, for example, if you probably guys have doing internships with different companies, most of these companies give you a laptop, and all the ports, all the USB ports, all the input-output ports of this laptop is either monitored or they are usually encrypted. So, for example, if you're trying to copy a file into your USB thumb drive, it's copied it, but it's going to copy it encrypted. And unless you have the key, you have no idea what that value is. Okay. And now imagine that there is a rogue employee in this company that really wants to steal this design file that exists in this laptop. What the attacker can do in this case is using physical side channels to exfiltrate that data. Okay? So remember we said that, for example, if I do if then else, the signal that I'm getting is different. What the attacker can do is similar to the way that digital side channels create some sort of a protocol between the sender and receiver. The attacker, instead of sending this information to the USB thumb drive, the attacker can actually create some sort of a code, a transmitter code inside this computer that, for example, let's say it reads a list of zeros and ones. These are the actual sensitive data that it wants to extract. What it does is basically saying that, okay, if for some reason I can detect if then else, what I would do is that if the value is equal to 0, I'm going to take the if. If the value is equal to 1, I'm going to take the else. Okay? And I'm just going to keep repeating this. So basically what will happen is I have this sensitive list. I have this list. My iPad is probably also being tracked because it doesn't work. But I have this list of sensitive values, and then let's say each one is just 1 bit, 0, 1, 1, 0, whatever. And what I would do is that I have this piece of code that reads this value 1, 1, 1. And if this 0, I just runs a piece of code for 0, and I run another piece of code for 1. And this creates signal number 1, and this creates signal number 2. Then what I'm going to do is that I'm going to have a measurement equipment outside this computer, sitting somewhere, receiving these signals. And here I'm going to have a receiver that understands the difference between this and the difference between this. So I'm going to go through this, create these two different patterns. On the receiver side, I'm going to collect this and I'm going to kind of like demodulate this. So I'm going to translate this. And then what I'm going to reconstruct here is the same 0, 1 pattern. Okay? So why would I do that? Because this computer is air gapped, so I cannot just say that, oh, this list I can, email it to myself, or I can use web, or I can use USB to send this information out. So a very quick way of exfiltrating this information is that I'm writing this very tiny piece of code. I create this physical side channels information like the power, it could be acoustic, it could be anything. And then I'm writing this simple receiver signal also, which is completely sitting outside this computer, has nothing to do with how the computer works. And then I'm going to basically replicate this list here. All right. And this way, kind of circumventing the air gap as well. So regardless of how much security you put into this system, none of them will work because I'm just using the physical characteristics. Does that make sense? And then you can basically use any sort of channel here you want. You can use power, you can use electromagnetics, you can use acoustics. For example, there's a very nice paper that just says that the speed of your fan can be used for like superheating it. So basically the fan, if it starts, creating lots of noise, I'm sending 1. If the fan doesn't make any noise, I'm sending 0. And all I need to do is that having a microphone sitting next to your laptop and just recording this signal for maybe like a 1 minute or so. Then I'm going to go back and say that, okay, for every like maybe millisecond, I'm going to just chop these signals into 1 millisecond, portions. I'm just going to see whether this was a high, fan or low fan sound. If it's high, it was 1. If it was low, it was 0. And very simple, as that, I can say what value has been sent. And for 1 minute, for example, I can collect hundreds or thousands of bits of data. And all I did in the laptop side was just playing with the fan speed, and that's all I did. Okay? That's it. So this is the story of covert channel and attacking covert channels in air gap systems. Any question here? So the final thing is, in the same realm of side channels attacks, there's another group of attacks called fault attacks. Generally, a fault attacks is instead of leveraging the physical characteristics of the system to exfiltrate something, use the physical characteristics to create a fault to the system. So remember, one of the papers early on that we discussed was that for Intel SGX, people have found that if they reduce the voltage significantly, they can actually flip bits, right? So that was one example of these false attacks. There it was more of a digital problem, but here we're basically saying that if I, for example, change the temperature, change the voltage, change, the way that I access the system and so on, I can actually create the faults. And how does that fault can help us? Fault can help us in various ways. If you recall, the confidentiality, integrity, and availability, all of those things can actually be impacted by the fault. Mainly availability and integrity, because of those main 2 things that faults can equal. Okay, so an adversary all it can do is that by changing some physical characteristics, it just make sure that your system doesn't behave normally as it should. There are multiple different, examples for fault attacks. If you're interested, go and take a look. There's a very famous one called Rollhammer, which all it does is just keep accessing your DRAM, and they found out that if they're accessing a specific line in DRAM, if they access, for example, this line in DRAM, what would happen is that the neighboring lines will start flipping, because of the magnetic impact that they have on each other. So I keep writing into this line, But these lines the bits in these lines start to flip. And this could create lots of challenges for modern systems. And I never have access to this line, but I access to this line. But since this just neighbored with the same line in my DRAM, I can actually attack. There is laser attacks. There is sensor attacks. There's a whole bunch of different physical attacks that create faults in the system. If you're interested, go and take a look at them as well. I think one of the paper presentation will be about these false attacks. So we're going to learn more about them. All right. One last thing is that side-channels can actually also be used for useful purposes. Just generally, given that you get these physical signals, what you can do is actually use them for example, monitoring the behavior of the system as well. And that's it for both physical and digital. Again, the key takeaways is that physical side channels are becoming more and more physical these days. And the reason that it's more and more critical is just there are more devices available in the environment. In the past, it was like one computer stored in this one entity. But these days, if you go to a coffee shop, there are hundreds of computers next to you available for you to do that, right? So we need to pay more attention to the physical attacks as well, right? So that's it for today. Thank you guys for listening, and I'll see you on Tuesday.